Hello and welcome to another video. I'm not sure what video this is, but I feel like it's video at least 20. So before we fill in this slide, which reviews what happens on the lagging strand, I want to review again, because I'm not quite sure if we get it, why replication has to be different on the lagging strand compared to the leading strand. So if you have another separate sheet of paper, I would get it out right now. Or you can just listen and maybe you understand, but there's no space to write this, so if you want to get another piece of paper and then staple it to this packet, that might be a good idea. So, this is a replication bubble that I just drew, or pause the video while and drew it, to not waste the time. So you can draw it if you'd like. And the first thing we need to discuss is where replication is going to start on each strand. So if you remember, DNA polymerase, and we're not worrying about the RNA primase right now, we'll bring that back in a second. Okay, so our DNA polymerase, so let's assume that there's already RNA primers on here, right? We're not going to worry about that right now. Okay, so DNA polymerase can only add to the 3' end of an existing strand. So this is the existing strand up here, and then this is the other existing strand. It always starts replicating by bonding nucleotides, or hydrogen bonding nucleotides, to the 3' end. So on this strand up here, it's going to start here and go in this direction so that DNA can be synthesized in a 5' to 3' direction. Okay. Now on the other strand, okay, it's going to start at the 3' here, and because it's 3', and start synthesizing DNA in a 5' to 3' direction. Okay. Now, so far no problem. This is the problem, though. Why we have to do replication 2 different ways. The fork is opening in this direction. Okay? So this can just go on forever and replicate till the end. However, on this strand, it continues going, and then it's going to get to the end, and then this is going to open, and it's going to have to go back and make a new strand. So the bottom strand, which in this case is the leading strand, will continuously go. The top strand in this case, which is the lagging strand, has to replicate the DNA in fragments. One thing that is always true, okay, is that the leading strand is always going in the direction in which the fork is opening. So this is the leading strand, because the direction of the DNA synthesis is in the direction at which the fork is opening. And the lagging strand is always going in the opposite direction. Okay, I know that's hard, okay? On the do now tomorrow, which I think is going to be really short, in the end you could just memorize that. You could just memorize that the leading strand is always going in. Can I have your... I will start again, because even the announcements even interrupt me while I'm trying to make videos. So what I was saying is that you could just memorize that the leading strand, which is synthesized continuously, opens in the direction at which the fork is open, or goes in the direction at which the fork is opening. And the lagging strand, okay, which is synthesized discontinuously or in fragments, and those fragments are called Okazaki fragments, okay, that replicates away from the opening fork. So if you wanted to, you could just memorize that. So now we're going to review the steps of replication on the lagging strand. And remember, the lagging strand, okay, goes in the opposite direction. I can't spell goes. In the opposite direction of the opening fork. And it's synthesized discontinuously. So I'm back in PowerPoint mode, so I don't want to write all the steps, because my handwriting is horrible, and you will better be able to read it. So I'm going to go through the steps and discuss them, and go back and forth to the video, a video that will help you explain this. So if you need to pause the video, while you're writing the steps, pause the video. So the first step, as it was on the leading strand, is that RNA primase adds an RNA primer. Okay? Then the second step is that DNA polymerase 3 makes an Okazaki fragment, with DNA nucleotides. So we're not going to go back to the same video that we started with. We're going to look at the bottom strand. Remember I told you not to look at the bottom strand? We looked at this top strand here. Okay, now we're going to look at the bottom strand. I'm going to click play, and you'll see on the lagging strand we have so the red was the RNA primer added by RNA primase, and then here is DNA polymerase. Okay, and DNA polymerase is now going to add the DNA. Okay, now notice that it went to the end. Okay, so we're going to go back to the PowerPoint. So we have our RNA primer, and then we have DNA polymerase, which added the Okazaki fragment. And you'll see that the fork also opened more over here. So, and this is continuing. This is continuing in this direction. But now, if we go back to the slide, we'll see, and now you can see all the steps. You saw the fork open more, okay? And then we're going to repeat steps 1 through 3. So RNA primase is going to add another primer, and then DNA polymerase 3 will make another Okazaki fragment. So if we go back to this is annoying, flipping back and forth, I apologize. If you go back to the thing, you'll see here is the second primer, and then we're going to add another Okazaki fragment. Okay, now, you'll see this is DNA polymerase 1, and what DNA polymerase 1 did is remove the primers, and it's going to do it here too, remove the primers and replace them with DNA. And the last thing that we got to do is that our green friend, DNA ligase, okay, is going to seal the ends of the strands. Or bond the strands together. It's really forming what is called a phosphodiester bond between the phosphate and the sugar of the Okazaki fragments. And you'll see that ligase will do it here as well. And then it's done. So if we go back to our steps, we have our final steps here, where DNA polymerase 1 removes the RNA primer and replaces it with DNA. And then last but not least, our enzyme friend DNA ligase finds the Okazaki fragments. When you're doing that, what the DNA ligase is actually doing is bonding the sugar of one Okazaki fragment to the phosphate of the other fragment. And then the process is done. The reason why this is called the lagging strand is that it occurs much slower than the leading strand. The leading strand just continues going. So once again, I got interrupted. And I forgot what I said last, so I'm going to repeat it. So the lagging strand is called the lagging strand because it occurs much slowly with the Okazaki fragments than it does with the leading strand, which just continuously goes in the direction of the fork. So that's why it was called the lagging strand. So at this point, we have all these things. I'm not going to do this. At this point, you should be able to write next to them what those things do and their purpose. Okay, notice that we have the leading strand opening in the direction of the fork, going in a 5' to 3' direction and adding to the 3' end of the existing strand. And then we have the lagging strand, which is synthesized in fragments, okay, going away from the opening fork. Okay, if I were you, I would make sure that you understand what all these things do and write them here, hopefully without looking. Last thing, which is not that important, but just the difference between DNA polymerase 3 and DNA polymerase 1, you can see the guys who discovered them. DNA polymerase 3 is the one that adds the bases very, very quickly after the RNA primer is made. It can replicate bases about 1,000 bases per second. Okay, it's the enzyme that mainly builds the DNA. DNA polymerase 1, okay, is the one that takes out the RNA primer and places the DNA in there. It also functions in repairing DNA when the DNA is broken or DNA is damaged. Okay, and it functions much, much slower, only 20 bases per second. All right, go answer the guide questions. Have a good day.